Hi, let us continue with our discussions about the design of reinforced concrete packed footing subjected to axial load together with the moment acting in the major axis. Previously, we talked about checking the shear resistance of the shear plane, which is located at a distance of 1d from column face. We are checking the shear resistance at this plane and also this plane, representing the major and the minor axis. We need to ensure that the shear resistance, which is VRDC, is greater than the shear loads as a result of the stress acting at these regions. Next, we're going to deal with the punching shear located at the perimeter of 2d distance from the column face, as this is another way that a packed footing can fail. In order to do so, we need to first determine the locations of this 2d perimeter. 2d here represents 2 times the effective depth. But if you look at the calculations previously, we have the effective depth for the major and the minor axis differ slightly. This is due to the arrangement of the reinforcement bar, where the secondary reinforcement bar is sitting on the primary reinforcement bar. Now, in the process of calculating the packed footing, especially for us to compute the effective depth, we use the average value of the two. That means the D in the major axis plus the D in the minor axis divided by 2, that gives you the D average of 488 mm. 2 times this 488 mm, it will be 976 mm. We will need to check whether these parameters fall within the area of the packed footing. If this 2d parameter goes beyond the packed footings region, then you don't need to check for the 2d parameter punching shear. How do we know whether it is within the packed footing or outside the packed footing? We need to first determine this distance and this distance, which are the Z1 and the Y1. We have calculated the Z1 and the Y1 previously. This was calculated by taking the width in the major axis, which is 2.4 meter, minus the width of the column, which is 300 mm, divided by 2, that gives you your Z1 equals to 1050. The 1050 is greater than 2d. That means you know the parameter of 2d shall go somewhere here within the Z1. How about the minor axis? Take the width of the packed footing, which is 2.2 meter, minus the width of the column in the minor axis, which is 150, divided by 2, that gives you 1025 mm, and then check with the 2d. The 2d is smaller than this 1025. From there, we can conclude that this 2d parameter shear plane is within the area of the packed footing. As a result, we will need to check the shear resistance in resisting this punching shear at the parameter of 2d. First, let us talk about the principles of the punching shear. You will need to determine the shear force as a result of the punching shear. and this shear force is calculated from the soil pressures acting at these regions, the area of the peg footing outside of these parameters of 2D, and then this total shear force shall be divided by the shear planes of this 2D parameter in order to obtain the shear stress as represented by this equation. And then in the case that there is moment acting onto the peg footing, this moment shall lead to alterations in terms of the distributions of the shear stress, leading to an increased shear stress acting onto the 2D parameter plane. As a result, this shall be reflected in the factor beta here. Once we have calculated the shear stress, this will need to be compared with the shear resistance per unit area, and then we need to make sure the shear resistance is greater than the shear stress. This briefly explains the design process for the punching shear at 2D parameter from column face. Now let us look into the calculation steps. You are strongly encouraged to sketch the diagram. This shall help you to imagine how the failure looks like, so that you are able to generate these results easier. You need the U to calculate the shear stress, and this U is also used to obtain the factors representing the influence of the moment. This U will be the parameters of 2D from the column face. How do you calculate the U here? You may use this formula, or if you have difficulty memorizing the formula, you can actually find this parameter graphically. First, you need the dimensions of the columns. The column width 300 times 150 mm. Second, you need the dimensions of the D. Since we are talking about 2D, 2D is equals to 976 mm. Now, in order to calculate this parameter U here, we take 300 plus 300 plus 150 plus 150 plus a quarter of the parameter of a circular times 4 quarters here. Ultimately, we are referring to 2 times 300 plus 2 times 150 plus a circular parameter in the radius of 2D. That means you're going to get 2 pi times 2D. The 2D, it will be the radius of this circular, and eventually you will obtain U equals to 7032 mm. Next, you want to determine the shear force. The shear force is generated from this area of the peg footing. You will need to take the total area of the peg footing minus the internal area here. How do you determine the internal area? You may use this formula, but it seems complicated. You are recommended to solve it in the graphical manner. To determine the total areas within the parameter, you need the area of the column, which is 300 times 150. You need these areas, which is 300 times 2D. You have two of the same size. multiply 2. And then you need this area, which is 150 times 2D. You have 2 equivalent areas. That means times 2. Plus 4 units of the quarter circle area in the radius of 2D. Therefore, you will use the standard formula for the area of a circle, pi r square, and the r here, it will be equals to 2D. Sum up all the elements within, you get your internal area. Once you have the internal area, you take the total area of the peg footing, which is 2.2 meters times 2.4 meters, minus the internal area. Then you get the area outside of the parameter. Next, how do you determine the shear force? Since you have moment acting in the major axis, you are expecting that the soil pressure will look something like this due to the influence of the moment as reflected by the equation here. But if you see the equation here, what the moment actually do is redistributing the stress acting onto the peg footing. Initially, the stress is equals throughout the section due to the moment rotations. Let's say in this case is in the major axis. The stress redistributed. Some of the stress here will go to the other side, resulting higher stress in the area against the moment. This can lead to complexity for you to determine the stresses as a result of this area outside of the parameter. But you know by principle, let's say the moment is acting in these directions. Some of the stress at these regions will go the other side. Eventually, total stress will still be the same, only the stress is being redistributed. Therefore, you can use simple rules of thumb to calculate the shear force. Take the average stress throughout, multiply the total area here. That means you are taking the average between the maximum and the minimum stress. The stress is in the functions of kilonewton per meter square. It's an area stress. Multiply the area outside of the parameter of 2D, which is this. You get your total shear force. This total shear force, it will be this VED. You have calculated the U, which is the parameter of 2D, equals to 7032. You have also the D, which is taken as the average effective depth, equals to 488 mm. Now you need to determine the beta in order to quantify the influence of the moment onto the shear stress. The equations to determine the beta is given here, which you need to calculate the W1, and also you need the K here. The K is a factor due to this ratio of C1 over C2. You may refer to this diagram for you to conclude the C1 and C2. By looking at the directions of the moment, C1, it will be the column side, which is parallel to the moment, and C2, it will be the column side, which is perpendicular to the moment. Now coming back to this case, your moment is in the major axis. the column size which is parallel to the moment, it will be your C1. And the column side which is perpendicular to the moment, 150, it will be your C2. Based on the calculated C1 and C2, you have the ratio of 2.0. Refers to this table, C1 per C2 equals to 2.0 will give you the K equals to 0.7. This is how you obtain K equals to 0.7. And then you need to calculate the W1. W1, it will be in the functions of C1 and C2. Based on the C1 and C2 calculated, substitute into the equations for W1. Use the average effective depth equals to 488. You get your W1. Now you have the design moment, which is equals to 150 as given in the question. You also have your VED, which we have calculated just now, equals to 283.6 kilonewton. You have the U, which is 7032. W equals to this, and K equals to 0.7. Substitute the value into the equations, you get your beta in the major axis. Now you can find the VED in terms of the stress. The VED is calculated. U equals to this, and the D is the average effective depth. Beta we have calculated. Now you obtain your shear stress equals to 0.1247 Newton per mm square. You will need to calculate for the minor axis also. However, in this case, there is no moment in the minor axis. Without any moment in the minor axis, this whole thing will be equals to 0. And your beta will be equals to 1.0. You don't have to go through this process to conclude the beta equals to 1.0. Knowing the moment in the minor axis equals to 0. Then you use the VED divided by the U and also the D, 488. You get another shear stress. What you see here, the punching shear is more critical due to the moment. If the moment is acting in the major axis, theoretically you only need to check for the major axis. The minor axis is not likely to be the critical side. Now, if the moment is acting in the minor axis, then you will need to check for the moment resistance in the minor axis, as the shear stress is likely to be more critical than the major axis. And if you have the moment in both axes, then you will need to check for both axes. It is harder to tell which directions will be more critical. Now, if you are unsure about this, you can always check for both axes for all cases, as demonstrated here. Now that we have obtained the shear stress, our next step is to determine the shear resistance to see if we have sufficient resistance to take the shear stress. To calculate this, you may use this formula, which is in the functions of BRDC mean. Now, if you observe the formula, referring to our previous calculation step, we have already done calculating the VRDC mean while we are determining the shear resistance at 1D from the column face. The two formulas are the same. You may use directly the values that we have calculated previously. while determining the shear resistance at 1D from the column face. Of course, you can choose to recalculate again using the same formula. Substitute the K, FCK and BD based on our previous calculation steps. You need to be careful with this K here. Try not to confuse the K here and the K here. The K here is used to determine the beta that you obtain from table 6.1 in the Eurocode 2. This K is meant for determining the punching shear stress, which in the form of the beta and eventually convert it into the punching shear stress. You should not substitute this K into the equation here. The K that used to determine the VRDC mean is calculated on basis of the functions of D, which the K here should not exceed 2.0. Substitute the effective depth into the formula for the K. You obtain K equals to 1.64. Then you compute the VRDC mean. Having the VRDC mean calculated, VRDC mean is in the form of the load, which is kilonewton. We will need to convert this into the shear resistance in the form of the stress. To do so, we will need to divide the VRDC mean with BD. And where does this BD come from? This VD comes from the BD here. In another word, the punching shear resistance here is actually equals to this part of the formula. The B here depends on the axis that you are looking at. Let's say you want to determine the shear resistance in the major axis. You take the VRDC mean from the major axis divided by this width, which is 2.2 meter, and also divided by the effective depth, which is 488 as the average. Now, if you want to determine the VRD in the minor axis, take the VRDC in the minor axis divided by this width, which is 2.4 meter, and also divided by the effective depth, which is 488 mm. That gives you the shear resistance stress here. This resistance is later checked against the shear stress. The resistance should be greater than the shear stress. Therefore, we know that the punching shear resistance is adequate. In the case that your shear resistance is less than the shear load here, that means the peg footing would have failed due to the punching shear. To rectify this, you may increase the thickness of the peg footing. By increasing the thickness of the peg footing, you increase the effective depth. As your effective depth increases, the punching shear stress reduces. This leads to a higher chance of it to be less than the punching shear resistance. Also, by increasing the effective depth, you're actually increasing the distance of 2D parameters from the column face. Having these 2D parameters further away from the column face, you will have a smaller areas outside the parameters. You know that we determine the punching shear loads based on the area outside of the 2D parameter. Smaller areas means smaller shear load. This also leads to the reductions of the punching shear stress. Until you get a smaller punching shear stress as compared to the punching shear resistance, only then you can proceed with the following calculations, checking for the maximum punching shear at the column parameters.